Hello everyone and welcome to this module on Introduction to Continuum Mechanics. So this is the first video in module 3, which is basically the fourth chapter of the book. So far we discussed the deformation, the concept of strain, and we introduced several strain tensors. Uh, in the absence of force. But in this module and in this chapter of the book, we're going to include the concept of force, and we develop some other kind of tensors, which gives us, which actually lands us to the in the concept of stress. So we will discuss different types of stress tensors, as well as stress power, equation of motion, principal equations, and several other concepts. So first, we use the Cauchy stress principle to basically uh, develop the very introductory and very fundamental form of a stress tensor and a stress vector. And later we get into uh, the form and reference configuration, how we can use the form and reference configuration to represent different stress tensors and develop new concepts. So let's get started by the Cauchy stress principle here. So basically, the Cauchy stress principle will give us will result in the Cauchy stress vector as well as Cauchy stress tensor. This Cauchy stress tensor you might know from your course of strengths of materials or mechanics of materials, where you had sigma ij. So it was a second order tensor with 9 components. It was a symmetric tensor. Now we're going to introduce this and say how it was initially developed by Cauchy. So let's get started by Cauchy stress principle. So suppose you have a potato shape like this in the reference configuration. And in the deform configuration, you have this again, or let's say current configuration. You have this potato shape again. So this is the reference and this is your current configuration. And here you have your, let's say, x1, x2, and x3, the Cartesian coordinate system or your coordinate system here. All right. So far, as I already said, we discussed the concept of deformation in the absence of forces, and now we have forces. So suppose that you have some forces here, like F1, F2. Let's say that some of them are in tension. So F3 and F4. So if you remember from some other courses, you have this potato shape and you say that, okay, we have a domain gamma here where you saw a bunch of, symbols here. So you had some hashes here. It says that, okay, so you have some gamma u in here, and you had some continuous kind of, some subsequent kind of, arrows here, and said you have gamma t, and you have b like this, or maybe in this direction. It's not important, just b. You might come across to this figure in some courses. So basically, this B is the body force. So if you have, for example, your pen in your hand or your pencil, if you just put it on a surface on a plane, so there is a gravity force, a weight force, or body force we call. that is applied to this pen or pencil from the center of the earth. We call this gravity, right? So this B actually represents the body forces. They basically are applied to the whole structure, the whole pen or pencil, so the whole volume. Therefore, we call them volume forces or simply body forces. So B represents body forces. And here you have gamma T. Gamma T is basically the surface forces. So the forces that are applied to the surface. Gamma T. Surface force. And here you have this hash gamma U, which is basically the displacement, the boundary condition regarding displacement. For example, if you have uh, a cantilever beam like this, and here you have this boundary condition in here. So it is the boundary condition regarding the displacement. Sometimes we call this gamma t as natural boundary conditions. And this gamma u as the essential or geometrical boundary conditions. Essential geometrical boundary conditions. So for example, if you have this, for example, this cantilever beam in here, and you have this force, this uniform kind of force in here, you have gamma t in here, so you have the surface forces here, and you have your, let's say, your essential or geometrical boundary condition, gamma u, in here. And you have, for example, your body forces. For example, let's say that it is a one-dimensional kind of problem. So you have B, and here is your, let's say, X. So this is B is a function of X. So you have your body force B in here. This is just something that I wanted to mention, just in parentheses. So this is not something included in the book, but you may come across to some of these kind of notations in some other books. So I just wanted to show this to you. All right. So this is, yeah. All right. So let's get back to our, potato shape in here. So here we have this shape. Let's assume that we basically divided this into two parts, into two halves. So we have one half in here, and we have the other half in here. And this is F1, F2. For example, this is F4, and this is F3. Uh, let's suppose that we have this surface in here and here. This one, let's call this as S. This is the surface S. And this surface S basically includes a point P, as the book also used the notation of P. So I'm going to follow this kind of notation in here. And let us suppose that this P actually is a part of, the plane dA. So an infinitesimal part of the surface S. We can define a normal like n to the surface dA, also, which is normal to S. And also on the other side, we have the same point P, we have the same dA, and we have the same S, because and this is basically n. Let's call this positive. This one is negative, or vice versa. You can put this as negative and this one as positive. We assume that this direction is positive. This direction is positive. All right. So let me say that we have the same point P in here. So the Cauchy stress principle states that you have both body forces plus surface forces. So the the Cauchy stress principle says that since this dA, or the volume that embraces this point P, is very, very small. So you have very, very small, for example, dx1, dx2, and dx3, let's say. And since these are applied to the volume, so we can neglect these terms. So Cauchy's strain in principle says that let us neglect these terms, and then we have these surface forces. So these surface forces can be characterized through a concept of stress vector. So can be characterized via the concept stress vector. So all of these is basically the concept of, so the whole this is the Cauchy stress principle. Let me just bring this in here. So this whole is the Cauchy principle, stress principle in here. So suppose we're in, let's call this 1 and let's call this 2. So we are in the either lower or upper part of the domain. So basically the stress vector, this stress vector which is capable of characterizing the surface forces here, is defined as Tn is equal to the limit of the resultant force, so this point in here, So you have the point P. So this is dA, and you have some resultant force, for example, let's say in this direction, or maybe in this direction it's better. So you have del F in this direction, for example, which is applied to the point dA. This is dA, or delta A, let's say. As delta A goes to the point P, or as delta A goes to 0. So it becomes a point, basically. So this is the concept of the Cauchy stress vector. So if I just, so for part 1, this is for part 1. So if I write this for part 2, I get Tn is equal to, here I have, for example, something like this, del F, which is in another direction. So it is the limit of minus del F, because this is due to Newton's third law, the action and reaction. So if you have this positive, this one is negative, divided by the same del A, on this side, on the upper side, when del A goes to 0, so it becomes a point. So from here, we can include that, and this is, sorry, this is Tn on n negative, and this is n positive, because here we said that n here in this direction on the lower part is positive, and here n is negative on this direction. Therefore, we can see that Tn plus is equal to minus T n minus. Here we have on the upper part n is negative, and on the lower part n is positive. So you see that they have equal values, but their sign is opposite. We can simply expand this concept to the whole del S. So we can say that T is equal to the limit of del F divided by del S, which is basically the whole domain in here, as del S goes to 0. So it becomes a point P. This is the Cauchy stress vector. And this is the definition of the Cauchy stress vector in here. So maybe I should write here assumptions. So these are the assumptions that we made for the Cauchy stress principle. So we neglect the body forces, and we only included the surface forces. Now, here we are at the Cauchy stress principle. So basically, in Cauchy stress principle, we say that this T, this stress vector, it depends at a point, let's say at a point P, right? So we have a position and at time T, or let me write this as time. This is a vector, so T, maybe boldface T. So the stress vector at a position like point P. So we have x, we have a position, and we have a time, whether we are in a current configuration or reference configuration, or maybe a kind of configuration which is in middle, because we can put an infinite number of configurations between the reference and the current configuration. We can assume whatever kind of configuration we would like. So this is a stress vector. Just shift this in here. This is a stress vector. It has same values ver. So you see here that it has same values on this surface, but it has the same values in here, but with opposite on the upper surface with opposite sign. So here, what can you see? Which is common for all the traction, or sorry, for all the stress vectors on this surface. So we can see that they have a normal n, which is positive, and also they share the same plane. So they're all on the surface S, for example, on the plane A, for example. So one, it is tangent, it is tangent to the plane, it has a tangent plane to point P, which is the normal n vector. And also, they share, they are on the same, on the one side, it's better to say, on one side of plane. So they have the same n normal vector, and they are on one side of, let's say, on one side of the plane, because on the other side, they have the same value, but negative sign. And this basically is the concept of Cauchy stress principle. All right. So from Cauchy stress principle, we conclude that stress vector is a function of, so T, the stress vector, let me just shift this to the right. T is a function of position, time, T, and let's say that this is capital T. Sorry, this is boldface T. This is boldface T. It's a function of position T and also N. And remember here, we are in the deform configuration, small x. So Cauchy stress tensor is a stress tensor that assumes we are in the deform configuration. So we are in the current configuration. And here, we can further simplify this to a tensor T which is a function of x and t of position and time and n. Because here we said that they have the same values, but this is n, that this is the vector n that defines the sign of the traction. So we can take this out. This is basically, let's say, a boldface letter in here. So we can say that t, the stress vector, and here we have the normal vector. So if we have the normal vector of let's say of a surface, then we only need to find t to find the stress vector, this transformation. This is a linear transformation, which we will prove in the following. But suppose here that you have a transformation that transforms this normal vector to the stress vector. Basically, this t is a second order tensor which changes with x and t. It is a function of x and t. Function of position and time. So if you have a dynamic kind of problem, you see that every time your transformation is basically changing, or or from one part to another part, or from one point to another point, it is changing. So t is a second order tensor, which is a function of position and time, and we know this as uh, it it is called Cauchy stress tensor. And if you remember, this is the same as sigma from your mechanics of materials, where you had sigma ij, so it was equal to sigma 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and then 3, 3. We will prove that this Tij basically is symmetric, as you already saw in your previous courses, and we also show that this is a linear transformation. All right. T is a linear transformation. So for the proof of this, let us assume that we have a tetrahedron like this, and you have your coordinate system like this. This is a right hand side, x1, x2, x3, right hand basis. And here we have a very, very infinitesimal tetrahedron. So we have del x1 in here, del x3, del x2. And let us name this. So we have this as delta A3. This is, no, delta, yes, delta A3. This is delta A2, and this is, or let me call this is in this direction, so delta A3. This is in this direction, delta A1, and this is delta A2. All right, so we also defined the normals in here. So we have the normal in this direction is T. So this is N negative. So here we have TE3 negative. And then this is the normal in this direction is again minus N. So this is T. So because it is in this direction, normal to this direction, so it's like this. You have a plane like this. So T E1 minus, and then here you have T E2 minus, because you have a plane like this. So if you have a plane like this, the normal is in this direction. All right. So I guess that these are all the things that we need. So here I'm going to basically write the uh, the principle of linear momentum, or let's call it Newton's second law. So I'm going to write sigma F is basically equal to uh, MA. So here I have let's say T, the traction, times the area, and let me write this in here. This is a stress vector, or we call this traction. So I may use these, names interchangeably. So this is stress vector. T is also referred to traction. So del F is basically is the product of T, the traction or stress vector, and the area. And remember, I have also a face on the top. I will discuss this later. So let me write this. So I have T E1 minus. So I have here del x 2 times del x 3 divided by 2 plus I have T E2 minus. So I have half of del x3 and del x1 plus I have TE3 times this rectangular here. So half of del x2, del x1 plus I also have a plane here on the top part. So let's call this delta A n, and it has a vector like a normal vector like n. So plus T E n times delta A n is equal to MA. And M is nothing but, let me write this in here. So this is equal to MA. And here, M is basically rho V, the density times V. So let's write rho, and density is, so the density, the volume of this tetrahedron, which is 1/6 of del x1, del x2 times del x3 times A. So here you see that del x1 since finally we're going to say that all these dimension, they're very, very tiny. So they all tend to 0. And therefore, we can say that this side of the equation, which has, del x1, del x2, the product of del x1, del x2, and del x3, it it goes to 0 faster than these terms in here, because they are like two counterparts of del x1 and del x2, or del x2, del x3. So we can say that 1/6 del x1, del x2, del x3 goes to 0 faster than these terms in here. All right, so we can say that this is equal to 0, and we can assume this to be 0. So then what we have is basically t e minus 1 del a1. So I'm not going to write this again as this, plus t e2 del a2 plus t e3 minus del a3 plus t en d delta n is equal to 0. We also have this normal vector here, n, for this n, this n is basically n1 e1 plus n2 e2 plus n3 n3. And we also know that n1 is basically, since we have this surface on the top in here for delta an, so we can write n, n1, n2, and n3 in the form of delta a's. Like n1 is delta a1 divided by delta an. So they are both scalars. So they give us n1, n2 is delta a2 divided by delta an, and n3 is delta a3 delta an. So if I substitute 2 in 1, I get t e1 minus, so instead of del a1, I write n1 delta an plus t e2 minus n2 del an plus, so instead of delta a3, t e3 minus, I write n3 delta an plus t en delta an is equal to 0. So since delta an is not equal to 0, so I can just remove this from this side of equations. So I get t e1 minus n1 plus t2 minus n2 plus t e3 minus n3 plus t en is equal to 0. And here, if you remember from here, we had t n minus, it was equal to the minus. So if I just bring this in here, it was minus, equal to minus of tn plus. So I can rewrite this, since t e minus 1 is equal to minus t e1, and the rest. So we can write this as minus t e1 n1 plus, sorry, minus t e2 n2 plus t e3 n3 plus, sorry, this is minus ten is equal to 0. So I can write this, if I just factor out this minus, I can write ten is equal to te1 n1 plus te2 n2 plus te3 n3. And I guess that I have to write this ten in the form of t, capital T and n, right? So we also know that we have n, which was equal to n1 e1, this was a vector, plus n2, this is also a vector. So I'm not going to write these arrows and heads in here. N1 e2, n2 e2, and n3 e3. So if I have both sides of this times n, so this becomes tn, this is scalar, so this is te1, n2 te2, then n3 te3. So if I compare these two together, so 3, 4, we get ten, or simply n is equal to tn, and also ten, uh, te1 is equal to te1, te2 is equal to te2, and te3 is equal to te3. So we get, therefore, we can conclude that T is a linear transformation. So if you remember, a linear transformation was something that could fulfill TA plus B equal to TA plus B, which is something we got here, and also T alpha A was equal to alpha TA. So if I put, for example, an alpha here at scalar value, so I can get this alpha all over here. So therefore, T is a linear transformation. So I can say Tn is equal to Tn in, let's say, in the tensorial format or notation. I can write this as, so I can simply write this T, small t. This is a vector, Ti is equal to Tij and j. This is the initial notation. And in the matrix format, I can write this as a vector is equal to T times n, or maybe it's better to write it like this. Curly brackets to indicate that these are vectors or first order tensors, and this is a second order tensor. And this is the matrix notation. There's an important properties here. So if you notice here, we have Te1 equal to T the transformation E1. We already wrote this from the first module or the second chapter of the book. T Ji E J, where J was 1, 2, 3. So 1, 1 E1 plus T 2, 1 E2 plus T 3, 1 E3. This was TE2, TJ2, EJ was equal to T 1, 2 E1 plus 2, 2 E2 plus T 2, 3 E3. And then we had TE3, which is TJ3 EJ, which is equal to T 1 3 e1 plus t 2 3 e2 plus t 3 3 e3. So this is the reason that we basically filled in the tensors vertically, if you remember, because we have here Tij nj. So we basically transform the unit vectors from one base to another base using these rules in here, and that's why we write t if we fill in this tensor this the components, the elements of t vertically, then we will have tij and j. Otherwise, if you, for example, fill in this transformation t horizontally, then you have to write ti is equal to t transpose ij and j, because now you have to transpose all the components to get the right answer. So it depends on how you transform your unit basis from one coordinate to another. So that's why some of the books basically write this as Ti is equal to Tji and J. So it depends how they basically follow these transformation laws in here. But since T is a symmetric tensor with real values, so this doesn't cause any problem because we know that T is equal to T transpose. Uh, so So far, we concluded that T is a linear transformation. And next, we're going to give you some tips about this T. I already told you that this T, I, J, and J. So it depends on how you transform your unit vectors. So whether you fill them vertically or horizontally, you need to follow certain rules. Here we use Tij and J since we fill in the T in matrix format vertically. And let's talk about different components here for T11, T211, and T31. So let's bring this tetrahedron again in here. So I may draw this once more. So this is x1, x2, and this is x3. So here we have T11, E1, then we have T21, E2. So here, and then we have T31, E3. So you see that this 1 is basically common between all the components in here. So this basically refers to the normal here in the direction of, let's say, x1. So here we have T11. And then we have T21. So this is T1 is the normal. So it is normal to x1. And then you have 2, which gives you the direction. And then you have T31. 1 is the normal. It indicates the normal. And then you have 3, which is the direction. So if you have 3, 3, 1, the first one gives you the direction, and 1 is basically the normal. Gives you the direction to the normal, to the plane. So for example, if you have T 2, 3, so you know that this should be in this direction. So it should be on this plane, on the lower part plane in here, for example, and it is in direction 3. So this is T, 3, 2. 2 is the normal, 3 is the direction. All right. We call these components here normal components, and we call these tangential components. So these basically T31, T21, they are in plane, and they gives us actually the shearing stresses, while this out of plane component, which is normal to the plane and it is out of plane, gives us the normal stress. This is something that you know from your mechanics of materials, where you show this with sigma, and you showed this with tau, if you remember. So next, we're going to show that T is symmetric. So the stress tensor is symmetric. So let's show the proof. So you remember from your courses in mechanics of materials that your stress tensor is basically symmetric. So you showed this using this kind of notation, that sigma 1 1, sigma 1 2, this is 1 2, 1 3, this is 1 3, and this is 2 3, this is 2 3. So this is symmetric. So now, I don't know if you proved this before or not, but using the Maxwell reciprocal theorem, we showed that, for example, sigma 1 2 is equal to sigma 2 1 in the last chapters of some of the books in for the strengths of materials. We have this theorem that shows if you have, let's say, a beam like this, and it is somehow supported like this, for example, and you use the principle of superposition. If you're not familiar with this, just assume that you're in the linear elastic region, where you have the Hooke's law. So you have sigma equal to E epsilon, for example, something like this. And you have very, very small deformations, and your load is also monotonic. So you don't apply the load instantly. So then you apply the load, for example, P1 and P2. So you first apply P1, and then you measure these deformations at 2 points, and then you had this P2. So when you apply P2, so it becomes, for example, here and here, then you superpose, or you sum these the strain energy of these 2 points, and finally you concluded that these two components are equal, or these coefficients are equal. So but here we're not going to use basically this Maxwell's reciprocal theorem. we're going to use the concept of momentum, the principle of momentum. You might have heard of this in your dynamic course, but if not, it's not important. Let's say that we are going to use the moments around a point, the moment equilibrium, for example, to find to show that the stress tensor is symmetric. So let me just bring this down. All right. So let's assume that you have a component here, you have an element here, for example, and this element here, uh, this is your coordinate. Let me just write it here. So we have x1 and x2. So we are in the plane x1, x2, and here we have, for example, t11. You know that this is normal, plus delta t11. This is T11 because we know that there should be a difference between this surface and this surface to have stress generated in this element. So that's why I put this delta T1 in here. Then we have T22 plus delta T22. And then I have T22 in here. Then I have the shearing stress. This is T. So the second subscript is 1, and this is in the direction of 2 plus delta T 21. Then I have T, normal is 2. It is in the direction of 1 plus delta T 1, 2. Then I have here T, normal is 1. This is 2. And here normal is 2. And direction is 1, T 1, 2 in here. And here, of course, I have delta x1, and here is delta x2. And here I have a point like O in here, in the middle of the, let's say, of the element. So I'm going to write the equilibrium here around the moment equilibrium around O. So I know that if I multiply this stress times the, let's say, the area, I will be able to find the a force, and then if I if I find the product of the force and the vector, so I will be able to find the moment. So this is equal to and remember here that this is, for example, x3. So then I have my third dimension here in this region, because for this part I need to I need to find the product of, for example, here I have del x1, I have del x3, the product of del x3 and del x2 for this surface in here. All right, so I have t, I have t11 plus delta t11. So they're basically and t11. This is basically crossing from the origin point O. So this doesn't create a moment. And also this holds true for t22 plus del t22 and t22. So they are also 0. Their moment is also 0. So I start with t 21 plus delta t 21 here times the area. This is the area. This is basically the area, which is the product of del x3 and del x2 times del x3, del x2. So this is the force. And then I need to find the moment. So it creates a moment around z. So maybe put this 3 in here. So, and the arm here is del x1 half. This is the arm. So next, I have this t to 1, and let me assume that this is positive. So this moment is positive. Plus t to 1. So the area is the same, del x2, del x3. Then I have del x1 divided by 2. So next I have t12 plus del t12 plus del t12 and times. So now we have del x3, del x1 is the area, del x1, and then the arm here is this del x2 half. And here, since I assume that this is positive, so this becomes negative. Minus t12 del x3, del x1, del x2 half. This is basically equal to, so we have the moment here. So I have I, the moment of inertia, around, the third axis, I3, times alpha, the angular acceleration. So here I have I3. So if you just look at the end of some of the books in mechanics of materials or dynamics, so you will find this I3, sorry, in dynamic course. So you will find this I3, which is equal to 1/12 of mass times the area of here, the area of this part. So it is the product of del x, it is del x1 squared plus del x2 squared, not the area. And m is rho v, so it is 1/12 of, so I have rho, and v is del x1, del x2, del x3 times del x1 squared plus del x2 squared. So if you see, we have an infinitesimal element. So del x1, del x2, and del x3, they all go to 0. Therefore, we can say that I is 0. So we can basically neglect this part in here, and we finally say that we have 0 in here. So remember here that any kind of body force is also 0 in here, as well as in previous in the linear transformation we have a, for example, here. So if you put any body force, since they are in the since they are in the same magnitude as a, because they are applied to the volume of the continuum, so they can be disregarded, they can be 0. So I didn't write them down here, but they are already included. So for example, you have the body force in here, but this body force is 0 since it is applied to the volume. And we already said that the volume, the rate of the volume, actually goes to 0 faster than these terms. So that's why I neglect this in here in the proof of the linear transformation. I just forgot to mention this. This is also the same in here. So without the loss of generality, we can say that the body forces is actually disregarded. And so let us. So here we also have, del x3, del x2, del x1, this product. So let's let's neglect these terms also when they time this delta t21 or delta t12 because they are very, very infinitesimal, and they also they're very, very small, and they also multiply by a small value, so they give a very, very small value. So let us neglect higher order terms like, let's say, delta, for example, delta t12, del x1, del x2, del x3 divided by 2. Let's just disregard this, or we don't need these two as well. So let's assume that these are 0. So finally, what we get is t21. So we neglect these, and we have 2. So this 2 goes with this 2. It's not important. Then we have t21 minus t12 times del x2, del x1, sorry, del x1, del x2, del x3 is equal to 0. And since uh, this, let's say that this can't be 0, therefore t21, because this is the trivial solution. So t1, t21 is equal to t12. Sorry, since this can't be 0, uh, this can't be, sorry, this can't be 0. So this is 0, so we can say that t12 is equal to t21. So you can do the same. So following the same strategy, we get t13 is equal to t31, and t23 is equal to t32. So we can conclude that T is a symmetric tensor. So therefore, T is a symmetric tensor. All right. So we are basically at the end of this video, but there's something that I would like to mention about example 4.42. So here in this example, we basically have a transformation t. So it is 2, 4, 3, 4, 0, 0, 3, 0, minus 1 megapascal. And here we have this transformation, and we're going to find the stress vector, which is parallel to the to a plane, where the plane equation is, so the plane is x1 plus 2x2 plus 2x3 minus 6 is equal to 0. So in order to find n, this vector n, you can calculate the gradient of f. So to find this, we have 1, 2, and 2. Since this is normal, so the dimension is 1 divided by 3. And therefore, t is equal to this t in here, 2, 4, 3, 4, 0, 0, 3, 0, minus 1, times, let's put this 1/3 in here. So we have 1, 2, 2 here, so we have 1/3. And then if you do the multiplication, you get 16, 4, and 1 in here. So now you have t, the traction vector. So you have a plane like this, and this has basically t. This is the vector t. And this is, for example, n. It's not important. And here, what I'm going to say, uh, so you have the vector t. Let me just put this a bit oblique. This is t. All right. So now the book actually wants you to calculate the, let's say, the normal stress. So in order to find the normal stress, you know that this is n. And if you want to find the normal stress, you know that it is in the direction of n. Let's show this with, sigma n, for example. This is normal. So it's like finding the, sigma n here is basically equal to t dot n. Because if you remember, we had two vectors in here. If we had a and b, so basically a dot b was equal to the dimension of a times the magnitude of a times the magnitude of b times their cosine, the angle between them. So this is theta in here again. So basically this is the same. So sigma n is t dot n. And this actually comes from here. And if I rewrite this, t dot n is equal to n dot t, where this this t is tn. So you see that you get the normal stress. This is basically tnn, right? Where we call this sigma n. So sigma n is equal to 1/3 of 1641 dot n is 1/3, so this becomes 9, 1, 2, 2. This is 1 divided by 9. This is 16 plus 8 plus 2. And basically this become 2.89 megapascal, as the book already wrote. So if you, for example, want to calculate, let me just use another color. If you want to find, for example, tau, the shearing stress, you can simply write this as tau is equal to t minus sigma n. And since sigma n here is scalar value, so you need to put n in here. So you get t, which is 1/3 of 1641 minus sigma, which is 2.89 times, and here is 1, 2, 2, and you have 3 in here also, 2.89, 3, and you can calculate tau in here. So here you get t as a vector.